Ever wondered how a pilot adjusts the plane's speed to ensure a smooth landing, or how economists predict market trends? The answer lies in derivative calculus. This mathematical tool is a fundamental building block in a wide range of disciplines. From the physics that governs the universe to the financial models that power our economies, derivative calculus plays a critical role. It helps us calculate rates of instantaneous change, find maximum and minimum values of functions, and even model complex systems in artificial intelligence and machine learning. Over the next few minutes, we'll explore the concept of derivatives, their applications across various fields, and the advanced concepts that make them such a powerful mathematical tool. We'll also discuss how derivatives relate to function graphs and the crucial role they play in optimization problems. So buckle up as we are about to delve into the fascinating world of derivative calculus. At its core, derivative calculus is all about rates of change. Now, what does that mean? Well, imagine you're on a road trip. Your speedometer shows your speed at any given moment. That's an instantaneous rate. Derivatives work in a similar way. They help us understand how a function behaves at a specific point, or rather how it's changing at that exact moment. In the world of mathematics, we calculate derivatives using limits, a concept that allows us to zoom in until we're looking at a single point in time. It's like pausing your road trip at one precise moment to check your speed. So, what are we really doing when we calculate a derivative? We're finding the slope of a function at a specific point. This slope tells us the rate at which the function is changing. In essence, derivatives measure how a function changes as its input changes. From the speed of a car to the trajectory of a rocket, derivatives play a crucial role in physics and engineering. They're like a mathematical microscope, letting us zoom in on the world's movements and changes with precision. In kinematics, the study of motion, derivatives give us velocity, the rate of change of position, and acceleration, the rate of change of velocity. In dynamics, they help us understand how forces influence motion. But that's not all. Derivatives are also cornerstones of control systems. They're used to regulate variables like temperature, pressure, or speed in a system by providing feedback about the current state. This feedback loop allows for adjustments to be made, keeping the system stable and efficient. Without derivatives, understanding and controlling the physical world would be much more difficult. They're the invisible heroes, working behind the scenes in physics and engineering, helping us navigate and shape our world. Ever wondered how economists predict market trends? The answer lies in derivative calculus. In the world of economics and finance, derivatives play a crucial role. When we talk about economic growth models, derivatives help us comprehend the rate at which an economy is expanding or contracting over time. They allow economists to measure and forecast changes in GDP, inflation, and other key indicators. Then, there's cost analysis. Here, derivatives help in understanding how changes in production levels affect the total cost, ultimately influencing pricing decisions. And let's not forget about interest rates. In finance, derivatives are used to calculate how small changes in interest rates can have a significant impact on the value of financial instruments like bonds and derivatives contracts. So whether it's predicting the next economic boom or bust, pricing a product, or evaluating a bond, derivatives are at the heart of these calculations. Indeed, derivatives are indispensable tools in economics and finance. Did you know that derivatives can shed light on the shape of a graph? Indeed, derivatives are the secret detectives of calculus, unveiling hidden aspects of function graphs. They're like a magnifying glass, allowing us to examine the slope of a curve at any given point. Consider a roller coaster track. The steepness of the track at any point corresponds to the derivative of the function representing the track's shape. When the track slopes upwards, the derivative is positive. When it slopes downwards, the derivative is negative, but the detective work doesn't stop there. Derivatives also help us analyze concavity and inflection points. When a curve switches from concave up to concave down or vice versa, we've found an inflection point. This switcheroo is indicated by the second derivative changing signs. The beauty of derivatives is that they can reveal much about the behavior of a function. So the next time you see a graph, remember there's more to it than meets the eye. From maximizing profits to minimizing waste, derivatives are key to solving optimization problems. Now let's dive into how this works. When we talk about optimization, we're actually talking about finding the best outcome within a set of possibilities. Think of it like trying to find the highest point on a hill or the lowest point in a valley. But how do we determine these points? Enter derivatives. By calculating the derivative of a function, we can identify where its slope is zero. These points are our maximum and minimum values. Imagine you're trying to maximize the area of a field with a fixed amount of fencing. By using derivatives, you can find the dimensions that give you the most area. This application isn't just limited to fields and fencing, but extends to a myriad of real-world problems across diverse fields like economics, engineering, and even ecology. In short, derivatives are the secret weapon in optimization. From the growth of a population to the rate of a chemical reaction, derivatives are fundamental in the sciences. In biology, for example, population growth can be modeled using differential equations, which are built upon the concept of derivatives. By understanding the rate at which a population changes instantaneously, scientists can accurately predict future population sizes and make informed decisions about conservation efforts. In the realm of chemistry, derivatives play a key role in understanding reaction rates. By calculating the derivative of the concentration of a reactant over time, chemists can determine how quickly a reaction is proceeding. This information is vital in a variety of contexts, from the development of new pharmaceuticals to the creation of sustainable energy solutions. Derivatives also find applications in fields like genetics, where they are used to model the spread of genes through a population, and in geology, where they help predict how landscapes will evolve over time. Clearly, derivatives have a wide range of applications in the sciences. Did you know that derivative calculus is at the heart of artificial intelligence and machine learning? Now that might sound like a mouthful, but let's break it down. Machine learning is all about refining algorithms or sets of instructions to make predictions or decisions without being explicitly programmed to do so. And guess what? The process of refinement is fundamentally an optimization problem, which is where derivatives come in. Derivatives help us understand the direction and rate of change in a function. In the context of machine learning, they're used in optimization algorithms to gradually adjust the parameters of the model. This is done in order to minimize the difference between the model's predictions and the actual outcomes, also known as the error. Furthermore, in artificial neural networks, a type of machine learning model inspired by the human brain, derivatives are key in the process known as backpropagation. This is the method by which the network learns from its mistakes and improves over time. Without derivatives, the advances in artificial intelligence and machine learning would not be possible. Now let's delve deeper into derivative calculus. We've talked about the basics, but now we're going to tackle some advanced concepts. One of these is the derivative of composite functions, a concept that's closely tied to the chain rule. The chain rule is a technique used to differentiate composite functions, and it's an essential tool in calculus. Then, there's the numerical approximation of derivatives. This is an important aspect of computational calculus. It's used when we need to solve problems that are too complex or impossible to solve analytically. With numerical approximation, we can estimate the derivative of a function at a given point, which can be extremely valuable in many fields, including engineering, physics, and computer science. These advanced concepts allow us to take calculus beyond the classroom, applying it to real-world problems in a variety of disciplines. Indeed, the world of derivative calculus is vast and fascinating. So, why does derivative calculus matter? Well, let's take a moment to reflect on what we've discussed today. Derivative calculus is a fundamental aspect of mathematics, with a multitude of applications that extend beyond the realm of numbers. It's the mechanism driving the laws of physics and engineering, from the motion of planets to the design of intricate machinery. In the world of economics and finance, it's the tool that helps us predict economic growth and calculate interest rates. It's what allows us to interpret function graphs, find optimum solutions, and predict rates of change in various scientific fields. It even plays a pivotal role in the advancement of artificial intelligence and machine learning. But perhaps the most important takeaway is this. Derivative calculus is not just a collection of abstract equations. It's a powerful tool that helps us understand and navigate the complexities of our world. From the speed of a car to the predictions of market trends, derivative calculus shapes our world in countless ways. So next time you marvel at a plane's smooth landing or wonder about the future of the stock market, remember the power of derivative calculus.